It's time now for the very first keynote speaker today. It's my pleasure to introduce Dr. Savvas Raptis. Savvas Raptis is a researcher at the Johns Hopkins University Applied Physics Laboratory. His main research, his main expertise lies in multi-point, multi-mission data analysis and in space plasma modeling. His work is focused on using and combining different satellite datasets with computer simulation and machine learning algorithms. So thank you very much, Savvas, for being here today, and welcome. We are looking forward for your talk. Thank you.
Thank you. Thanks. So thank you everyone for being here. I will make this presentation, which is kind of a high-level presentation, as you will see. And I would like to thank, of course, people who helped me from Johns Hopkins University at the APL. And also big thanks to Gianni Lapenta, who passed away last year, because he was the first person who actually introduced me in this topic when I was a master's student in Leuven. So let me begin with a very high-level intro, and then I will go through some different examples from the fields of heliophysics and space weather that have been recently done. And then I will go into the main kind of topic, which is on board AI application. So I wanted to share this slide because this is actually the slide I used 3 years ago when I was doing a guest lecture here at the KTH, where I actually said that AI is a term often used just to draw attention. And I think it's still kind of valid, although honestly, we are already in this stage, on this theme, where basically there is an even bigger AI boom lately, where everybody's talking about it. So I was kind of correct, but at the same time, I said that AI might be 10 or 20 years in the future, so maybe that's not necessarily true anymore. So back then, I also had this slide, which was basically a few of the topics in the field that people are very interested to use machine learning on, which is to predict, for example, energetic particles, coronal mass ejections, to find when we have geomagnetic storms, to classify different environments that we have satellites orbiting. And I actually searched what happened in the last couple of years, and many people have worked on those topics. So this is something that people have been looking at actively, and a lot of publications have been coming out, both in like changing the methodology, but also kind of changing the underlying physics that we understand about those things. And just to give an illustration of how many people are working on this topic, both across the heliophysics, but also astrophysics and planetary science, we get more and more publications coming out every year. So you see there's a clear trend, not only up to 2020, but even later, where people are using those techniques with AI, machine learning, and all the latest tools that you're all aware. And the reason this is happening is because we have many more missions compared to what we used to have. So we have the recent missions targeting the SWAN, which is the Solar Orbiter from ESA and Parker Solar Probe. But we also have new missions, relatively new missions like the MMS and other in the magnetospheric regime. And this is also true if you move to the other planets. So the planetary fleet actually from NASA and ESA are actually, it's huge. So you get actual observations in situ with many different spacecraft, and all this data have to be analyzed somehow. And those machine learning methods offer a way to combine those data sets in kind of a single methodology, essentially. In other words, learning how to use those algorithms and also like even more to apply them on board is beneficial not only for the Earth environment, but also for other planets. And when we're looking at the sun directly, either through images, as we will see a few examples, or with in situ observations from each instrument we have. So I want to highlight a few of the key results. What I had in mind was that there is already familiarity with most of the machine learning terms, like what's supervised learning, what are neural networks, and so on, and some basic understanding on space and solar physics. This might not have been a smart choice from my part, but I tried to use a few very simplistic definition on what I will be saying. So basically, for space weather, we study the effects that happen at the Earth. So the sun spits out particles, and we get different effects at the Earth and its technology. When I say heliophysics, I essentially mean all kind of analysis we do with spacecraft and simulation for our solar system. And when I say plasma environment, I basically mean that you have distinct regions where satellites orbit that have very different properties. And therefore, we want to have different kind of potential instrumentation or modes or ways to get the data from there. So I have the slides in a very simplistic format, which is how we impose a problem and then how machine learning was recently able to provide a solution to that problem. So one of the key problems we have in heliophysics is what type of near-Earth conditions we have for the solar wind. And this is key for space weather. So basically you have the sun, and as you get solar wind going through Lagrangian one point, it is still very far from the Earth. So we still need to know what happens in very near Earth conditions in order to understand and predict space weather phenomena. And we have some tools, but those tools are very simple, let's say. They do propagate the values, but they do not provide a coherent 3D picture like we use or we want to use. And very recently, a friend and a colleague of mine that we worked together actually worked in a very nice methodology where they used a probabilistic recurrent neural network. And basically, they took all the data we have in the history of at L1 and produced near-Earth solar wind observations. So this is a very simple, in a sense, methodology slide, but it shows that by using the history of data up to 2 hours before the observation we want, he was able to generate very nice distribution of the different properties. And you also see an example output metric at the bottom, where these are the y-axis is basically the model output against the actual observation. And since everything lies very closely, or relatively closely, to the XY line, it means that you have a very good accuracy between your target output, which was actually measured, versus what the machine learning model essentially had as a output there. Now, if we want to make this a step further, we can actually ask another question. What happens in another distinct plasma region? So again, the solar wind comes here from the sun, and we really want to know what happens from a space weather perspective, very close to the socket of the Earth. But what actually dictates phenomena at Earth, like geomagnetic storms, is what happens on the night side of the Earth in a plasma set. So this is a super important region to understand the underlying physics of storms and also to get insight about the magnetosphere system of the Earth. So if we use a very similar approach to the one we used before, we got pretty similar results. And this is just to illustrate how better machine learning models can actually perform compared to our baseline models. So here I have 3 scatter plots from an ongoing project that I have, where this is what we call Tsiganenko-Mukhai model. It doesn't matter. It's a more, let's say, simple model. And this is, again, the model density against the real density that we measured. And you can see that the points for the neural network approach were much closer to the XY line, indicating that we get a better result overall. And you can see also from the metrics on the right that by using a simple feed-forward, fully connected neural network with a couple of layers and a few neurons, we get a much better result compared to any kind of, let's say, simple linear model that we developed before. So let's go to another problem, which I think is very relevant for this kind of topic, to do on-board calculation. So there's a question like, where is the spacecraft located? And of course, on a fundamental level, we know the location of a mission, right? So we know that if we pick MMS, which is a mission orbiting around the Earth, we can actually follow its coordinates and see where it is at any time. But this is not everything we're actually interested in, right? So as I said before, by having distinct plasma environments, different kind of conditions, we care about where the spacecraft is located with respect to those different environments, right? So you can think that you have those, let's call them boson and magnetopoles. The underlying physics is not very important for now, but what I can tell you for sure is that by being in the solar wind or magnetosphere, so different regions, everything you measure is different. So you need potentially different kind of instrumentation, different modes in the instruments, different resolution, and so on. So we don't only care about where we are in coordinates, we care where we are in actual physical sense. As a result, you can see how different those orbits are that have actually color-coded with the different regions. So they do follow roughly the orbits and the expected location, but because those boundaries change dynamically in time, they are not exactly the same all the time. So you can see here, the blue color, which is the magnetostate, is shifted a bit in and out every time. So we care about that information. We care fundamentally for this. And there have been many ways to do it. Many people have tried to do that in the last couple of years. And as you can see, the orbits can look very messy, and you can have very different kind of locations for the spacecraft. And here are a few of the examples. There was a recent paper that we worked with, which basically, rather than putting a supervised learning approach, we used unsupervised learning, which seems to be working very well because you can actually derive the feature space from the MMS mission, for example, and try to apply the same features in other planetary environments and see if actually that plays out and we're able to generalize to other missions. Also, there is another question we are trying to address where, with all that information we gathered, whether we can actually produce synthetically generated data to study other systems, like other planets, exoplanets, astrophysical systems, and so on. But this is to be determined. It's super early in the project. And now we have one more problem, which has to do with where do we need data with high resolution. So this is something a lot of people have worked. You can actually see the difference in those two plots, right? So A is what we, for example, in a mission we always have. So it's kind of low resolution data. And you can actually see that this red shaded region on A is the same time as shown in panel B. So we can actually have much higher resolution if we really need it. The question, though, is that when do we need that? So we cannot really downlink to the Earth everything, right? We cannot really put all the data from the satellite to the ground. So we need to prioritize and find when we actually need this kind of high resolution data capabilities. And some people have already tried to use an LSTM neural network in order to approach this problem. So again, the methodology here is a model where it has kind of, let's say, a standard LSTM architecture. And the idea here is that they want to copy the behavior of what manually scientists would pick. And you can see here at the bottom panel on the right, what would be the manual selection that people did against what's the selection of the model. So although this worked relatively well, the fact that next week I actually have to go through this process myself and do it manually means that we still cannot fully rely on the model itself. So we still have, and prefer most of the times, to have a manual verification for it. But this, for example, as I will show soon, can be super useful if the downlink capabilities are not very easy to do. So MMS orbits the Earth and we have enough time to get the data down, look at them and pick what we want. But that's not always or necessarily the case. And one last problem that I wanted to show you is whether we can actually produce synthetic data from machine learning and from data observations. So without going into details about what we see here, I can just tell you that you can have two spacecraft, and in between there is a very weird environment, what we call the shock, a Bose transition. And essentially one of the spacecraft which is upstream sees some kind of signature, while the other spacecraft which is downstream sees another one. And it's interesting because our theory can produce some kind of bulk quantities on how things change between that. But there are those features that while we know they exist, we don't have a very well-working theory in order to predict them between the two different interfaces of the spacecraft. So we can actually use a neural network to try to create artificially or synthetically these data sets by only looking at what happens in one side and actually trying to predict the other side. So here, the second panel is the artificial, let's say, or synthetic spacecraft, while the third panel is the actual spacecraft observations. This is very, very preliminary results, I have to admit, but essentially what you see here is a result from the test set. So we trained a neural network on many different years with many different spacecraft data, and we were able to kind of generate synthetic data that at least they form the features that we are interested to see. This, if done right, which I'm pretty sure there are many more things to be done there, can be super useful because it gives us context on location where we do not actually have spacecraft, but we really wish we did in order to understand the underlying physics. Now, there are many more results, right? So I didn't want to go through all those. I just listed a few of them. There has been a lot of progress in physics-informed neural networks and modeling, as you can see here from a few papers. There have been a lot of progress when it comes to predicting and forecasting, and also a lot of advantages on what we need to have machine learning ready data set, as they call it. So kind of a benchmark data set that we can all use in order to compare our modeling. And there are many, many more, but I didn't want to go too much detail on a few of those because the presentations afterwards actually focus on real scientific results that people have done on a few of those topics. But the main message is that, yeah, many things have changed. A lot of people work on this, but what are we missing? What is actually the missing link between what I showed you and what we want to do, essentially, with this workshop? And the problem is that most applications use what we call level 2 data and above. So those data are post-processed, right? They are data that we have already curated. They have been already calibrated. Everything is nice. You can import it in your cool pandas and PyTorch and TensorFlow models, and everything works fine. But this doesn't mean that it is the same thing as using level 0 data, which you usually have to rely when you are on board of a spacecraft. So there are people who have tried that. So, for example, a colleague of mine is doing an ongoing work where they use level 0 data from SDO, which is a mission basically looking at the sun and getting images across different wavelengths. And they were able to determine with level 0 data some very nice precursors from doing computer vision. So it's not really machine learning, but it's kind of traditional technique that works pretty well. And they were able to get a very good detection rate on when you will have a solar flare, which is very important for space weather effects, up to 70% 4 hours before the flare. However, there was a problem here, that their model was super lightweight and it worked perfectly fine. But when they tried to look if the power supply and the processing requirement on board is sufficient, they discovered that it is not. So their model was okay in theory, but in practice, they could not really do it on board of the spacecraft. And this brings me to this slide that there can be many applications that we can discuss, right? A lot of them have to do with processing data on board, with automating instrument operations, and with combining different data sets, for example, from different missions. And machine learning can be super useful for that. But there are many issues, right? One of the issues is that a lot of our modeling relies on having some Python script that have used level 2 data on the ground. And this is not the same as actually doing it on board. And I really hope in the afternoon session, people who actually do more of those can explain to me how they do it. There is another issue that the data that we have are basically uncalibrated data on board for level 0 or unvalidated. And this can be problematic. And also, most of the current hardware cannot really have enough processing power to really handle those kind of algorithms. So although I will show you a few examples on why it is very crucial to get this kind of technology, still there is a big problem. And I think what we need to do is to establish what requirements are needed in order to run those things. So I have another slide soon, but the main idea for me, or the main thought that I have after going through the literature and what problems we currently have is we need to show to the people what is needed for our algorithms to work there, so that in future missions we can have next generation processors that can handle those requirements and do not have to rely on very limited hardware. So this is an example case where we might actually need some kind of onboard computation. So this is the MagCon concept, magnetospheric constellation. And the idea there is that we would have 30 spacecraft in different kind of orbits at the Earth. And to have, like, for example, optimizing the orbital coverage of such a mission, one needs to do decision-making on the spot, right? So in those cases, you can have very useful algorithms to do that. And machine learning and AI would be very useful. This was a concept, but the combination of two different concepts, the MagCon and Paragon, is actually a mission now called LYNX, which was highlighted in the 2024 NASA Decadal Survey, or in simple words, most likely eventually will happen. So one needs to think whether in the future we can have a functional algorithm or case to demonstrate actual use of machine learning methods for 26 spacecrafts in order to optimize their scientific outcome. The same applies for smaller missions, which I mentioned a few concepts here. But of course, I would argue that the more spacecraft you have, the more useful those kind of techniques are going to be. I also want to discuss another solution, which I made this slide yesterday, that although I think on-board computation can be super useful, we shouldn't forget that there are missions that have what we call like real-time transmission. By real-time, I mean a few minutes, where you could potentially get data on the ground, do the computation, and send back the result. So this is not exactly the same, but it could work for missions that are close to the Earth. It's an important point to mention, though, that this needs to exclude any kind of mission that is going to be outside of the solar system, right? Because if your telemetry rate is huge, like if it takes very long time to get the data on the ground, you will not be able to do any decision making through that. So especially for missions that are very far from the Earth, one needs to think actually for a smart way to do all those things on board. And those are, this is actually my final slide. I put a few more of the ideas from the discussions I had in the last couple of weeks at APL. There are many things to be done, right? Processing, orbital formation and maneuvers. For example, do you want to do collisional avoidance? That would be very useful, I guess, for LEO or other kind of more close to Earth satellite missions. But also from a scientific perspective, you may want to change your mode in instrumentation. You may want to have separate objectives that change very fast in time. But there are still many open problems. And to be honest, I think the last point here is from what I picked up from engineers that I told the most important point, right? How do we actually wrap those like algorithms and models in the mission design? Like when I talked to a spacecraft engineer, I was actually trying to understand what they were looking for a week ago, because my knowledge on that is pretty limited. I hope to learn more from you guys. But he told me that if your application somehow saves mass, power, volume, telemetry, and in practice, if it helps us to reduce the cost, it might be doable to do it. Same happens if somehow your application enables new science. So if, for example, by using your code, I can make sure that scientists are going to have data that they didn't have before, and they can do interesting and cool stuff. But you just have to show it and demonstrate it. And I think we are at that stage right now where one needs to show what those codes are capable of, and also demonstrate to the people that are in the design phase of missions that it's worth it to put it there and actually take a risk in order to do that. So that's all I have. And
thank you very much, Savvas. We have 7 minutes for Q&A section. Questions or comments?
Thank you very much for the very interesting talk. I have two questions. So if you go to page 26, so that one, I'm not an expert on this, but do these spacecrafts that you're launching, do they have the capability to talk between each other and collaborate towards some kind of goal? Or
so that's a good question. I have to be very honest with you. I'm not sure. What I know, though, is that establishing a comp system between them would be super useful. I don't know if there's already something or an idea to do it. As far as I know, there is not. I may be mistaken. But as you already said, for determining and optimizing their behavior, they need to communicate with each other, or at the very least have a common kind of communication system to a place where they can do the operations there and back.
Because I guess the communication between them should be faster and down to Earth, and then ping-ponging, like coordinating things from Earth. Or
so you're going to say something. So
it's very problematic for them. You cannot get enough data rates
between them.
So on the ground, you can have a 30-meter dish, and then it's quite efficient because of this. But if you have a spacecraft, especially if it's spinning, your data rate is very, very low.
And then just a follow-up question, maybe not. In the introduction, you mentioned unsupervised learning. Have you seen any of that being pursued, and in what capacity, or in what's the aspiration there that people are?
So, I mean, I can tell you this project where basically there has been already a supervised learning effort to classify different regions, because we have done it by hand. Actually, from mistaking, you have done it by hand there. And then people, like there was a model developed based on this hand kind of labeled data set to derive a supervisor. But there you kind of go to this problem that any kind of error that exists in your hand labels propagates throughout your model's version. With unsupervised, what one hopes is that the actual data can generate, or with your help as well, generate a feature space where you can rely on. And there is another key factor here that if those features, for example, are general, they are part of a more statistical ensemble or distribution, you can potentially apply the same features to other missions and other planetary environments. Still, this will not be easy because there are different instruments and different kind of issues within the calibration between them, but one can hope that they are more easily generalizable compared to the supervisors.
Thank you. Other question, comments? Daniel?
You have shown in one of the slides, particularly, that the precision rate of detecting solar flares was 70%. I was wondering whether the current models that we have, they are good enough for the applications, because imagine that we have an earthquake and they can detect 70% of the time. But this means that a lot of times I will have a lot of costs for evacuation of people and so on, and nothing will happen. So if we could increase the precision, this means that we might need a lot of more powerful hardware, which means that we are a long way in actually having applicable results to the society. So what's the state on this?
So let me clarify. This is a project which main idea is to illustrate how much can be done with the level 0 data, with onboard calculation. There are much better models that are functional when it comes to already processed data that are on the ground. And since, well, solar flares are pretty fast in a sense that they are like X-rays essentially hitting the Earth super fast, but for the more like events like CMEs, it takes a very long time for them to arrive to Earth. So we have kind of a buffer time in order to do an even better prediction. And I would argue that we need more observations to get a better forecasting model, because this again looks at the sun, but we may want to have multiple kind of angles, multiple in situ observations in the space between the sun and the one another location in order to have a functional model. So yeah, it's a long way, but one has to start somewhere, I guess.
Thank you. Other question, comments?
I have one question. So you have all of this exciting work. How much data is open source? That's so that other people can. Is it fairly open source in the community?
Yes, especially the level 2 data that we primarily use is mostly open source.
Cool.
Easy to download, especially from missions like MMS, but also other missions have done a great job. It's very well curated and easy to plug in.
Even the raw data, the L0 or what?
No, the L0 are not necessarily easy to access in most missions. But that's why I guess to do those kind of applications and test them, it's good to be part of the mission or have someone who's part of the mission to help you test things out there.
There is also embargo time sometimes with a new mission.
I see.
But I agree, it's very much detailed. There are database, you can do very, very nice workflow. George? Oh, sorry, Panagiotis.
Concerning this work, the final outcome, you said that even though they didn't need to do any processing of the data,
they did processing of the level 0. So they did basically filtering to generate kind of max amplitudes to find the precursor, and then based on the combined, I think, mean filter divided by background, if there was a peak, they found it's well correlated and used it as a detection. Again, this has not been published yet. This is a result that were shown at the AGU last year or something, and I think they're actively looking for funding to do it on the last step.
But did they come, let's say, to a outcome that they would need specific amount of, let's say, threshold of resources in order to be applicable?
No, so the outcome was that there is not, that because the power and the processing is shared among the instruments in the SDO, it is not sufficient to run an algorithm dedicated for that task on board. I don't think they came with a conclusion on what they need, but it's on their to-do list, again, as soon as they find funding to do it.
That would be actually very useful for us.
Yeah.
That they're fine. Because indeed, we also have some data models that they're working mostly on level 2, and also we have acquired some data at level 1.5, let's say, and we do it in level 2. So indeed, there are data sets that are publicly available, you can acquire them really easily. But then we have this actual problem. We have nice, I guess they work, and then we have to simplify them, adapt them to be feasible to run.
And I think, especially this point at the bottom here, that one needs to establish what requirements are needed. And I think that point would be the most useful.
Thank you.
Yeah, thank you, Payas, to bring it up. I think, one of the reasons of this meeting also to foster collaboration. I think, we can talk also, include Savvas and Giacomo also today, more on the project side to see how we can cross-fertilize with the results. So if there are no questions, Yuri?
Going back to this unsupervised learning, yes. So if my kind of initial experience was the things you find there, because it doesn't have any intelligence, yes, this unsupervised learning, that you find things like mode switches most of the time, so artificial things that are most prominent in your data, yes, not the real stuff. So how do you approach it?
So this was done again with level 2 data. But also, like, in this case, there was a lot of filtering afterwards. So we didn't just took whatever the unsupervised learning spit out and went with it. So we had, again, to kind of look. One has to have a trained eye to look at those caveats and filter them out through some if statements at the end. So it's not out of the box solution, but it did most of the work.
There are no comments. Let's thank Savvas again. We have now 3 talks. The first talk will be Dr. George Milosevic.